Welcome back to the Deep Dive. We're here to turn complex research into, well, actionable insights for you. And today we're looking at something that could really change the game for large language models. We're talking about LLMs that don't just learn, but actually figure out how to learn better all by themselves, continuous adaptation.
Exactly. We're digging into a really interesting framework called self-adapting LLMs, or SEAL. It's from a new paper out of MIT. And this isn't just, standard fine-tuning. It's about giving the model the actual capability to make its own training data, maybe even figure out its own optimization strategies.
Okay, right. Let's break that down. So the core problem they're tackling is that these incredibly powerful LLMs, they're kind of frozen once deployed, right? They're great, but they struggle to keep up with new info or new tasks without a lot of human effort, a lot of intervention. I like the analogy used earlier. Think about a student cramming for an exam. They don't just passively read the notes. No, they rewrite them, condense things, maybe make flashcards or diagrams. They actively restructure the material to learn it better, their own way.
That's a perfect analogy, yeah. Most LLMs today just kind of consume data as it comes. SEAL asks this really fundamental question. What if the LLM could actually mimic that human process? What if it could generate or transform data into the format it learns best from? So our mission for this deep dive is really to explore how SEAL pulls off this self-directed adaptation, look at the results they got, and think about what this means for AI going forward.
Okay, so how does this self-adaptation work mechanically? The paper talks about self-edits. What exactly are those? How do they drive this whole adaptation thing?
Right. So at its core, SEAL is basically a two-loop system. You give the LLM, let's call it LLM, where P passes all its parameters, some new input. Its first move is to generate something they call a self-edit, or SE. And this isn't just like the answer. It's a directive, an instruction for itself.
A directive. So is it like generating code or more like natural language instructions? Can you give an example? What would a self-edit actually look like?
It's mainly natural language. Think of it almost like a little script or a detailed command the model writes for its own next step. So an edit might be something like, okay, read this document, pull out all the names and what they did, then write a short summary of the main point as bullet points. That could be one. Or for a totally different task, maybe image processing it could generate. Apply random rotations between -10 and +10 degrees, flip horizontally sometimes, then fine-tune for 3 epochs. Use Atom, learning rate 5e5. It's instructions for its own process.
Okay, that makes it clearer. It's an internal instruction set. But just having an instruction doesn't change the model itself, right? How do these edits lead to actual persistent updates? And crucially, how does the model learn to generate good self-edits, ones that actually help, instead of just random changes?
That's the key. And where the second loop, the outer reinforcement learning loop, comes in. It's absolutely critical. So the model generates an SE, that's its action. Then that specific self-edit is used in an inner loop. This is usually a supervised fine-tuning step, an SFT step. This SFT step updates the model's parameters, creating a new version, let's call it LM prime. And then the performance of that updated model, LM prime, on some downstream task that determines the reward signal for the outer RL loop. So basically the model gets positive reinforcement if the self-edit it generated actually made it perform better on the task. Interestingly, they found that standard RL methods like PPO, proximal policy optimization, were actually kind of unstable here.
Oh, really? PPO is pretty common. Why unstable? And what do they use instead?
Well, yeah, PPO can be tricky to tune sometimes, and maybe a bit much for this specific setup. It can kind of oscillate when learning actions in these really complex spaces, like, training an entire LLM based on its own instructions. So instead, they went with something called RESTM. It's simpler, more robust maybe. It's based on filtered behavior cloning. So RESTM isn't trying to discover the absolute best action from scratch. It watches the results of the self-edits the model generates, and then it learns to just copy and filter the ones that actually worked well. It focuses only on reinforcing the edits that demonstrably improve performance. Much more stable learning signal.
Right, so it's learning from its successes. And this whole cycle, as the paper points out, is really a form of meta-learning, isn't it? The model is literally learning how to learn better, optimizing its own learning process. Okay, we've got a handle on the how. Let's talk about the what. What can SEAL actually do? One of the big challenges, maybe the biggest with LLMs, is keeping them current, adding new knowledge without retraining the whole thing from scratch. So how does SEAL handle this? This idea of knowledge incorporation, getting new facts into the model's weight so it just knows them without needing the original text anymore.
Yeah, this is a huge application area. Normally, you might just fine-tune on the raw text containing the new facts. But SEAL does something different. It suggests fine-tuning on synthetic data that the model generates itself. Specifically, it generates implications based on the new passage. This builds on some earlier work showing that training on these kinds of derived implications can actually be more effective than just raw text or even standard in-context learning.
Wait, so the model reads the text, generates a list of implications like logical takeaways, and that list becomes its own training data. That's really clever. Why implications? Why is that potentially better than just learning the raw text? What's the intuition?
Well, the intuition is that generating implications forces the model to actually process and synthesize the information, not just memorize the words. It has to understand the core meaning and the logical consequences of the text to generate good implications. This process seems to create a deeper, more generalized internal representation of that knowledge within the model's weights. It's less about surface memorization and more about internalized understanding, which helps with recall later.
Okay, that makes sense. So how did it perform? What were the results when they tested this, especially compared to other approaches?
They used a squad task, but critically, without giving the model the passage during testing, so it had to answer from its internal knowledge. The base model, Quinn 2.57b, which is a decent but not enormous model, started at about 32.7% accuracy. Fine-tuning directly on the raw passage barely moved the needle, maybe to 33.5%. Pretty negligible gain. Now, using synthetic data generated by a much larger model, GPT 4.1, that pushed the accuracy up to 46.3%. That's a good jump. But here's the kicker. Seal, using just the Quinn model itself to generate implications and optimize through RL, got to 47.0% accuracy after only 2 iterations. So it actually outperformed the synthetic data from the much larger GPT 4.1. That really highlights how effective that RL optimization loop is. And they showed it wasn't a fluke, it generalized well when they tried it on a larger set of 200 passages in a continued pre-training setup, consistently doing better than the baselines.
Impressive. Okay, so beyond just facts, Seal also aims at few-shot learning. This is where a model has to adapt to a completely new kind of task using just a handful of examples. Super important capability. How does Seal tackle this? Especially on something tough like the RRC-AGI benchmark, which really tests abstract reasoning.
Right. For few shot, they use the test time training, or TTT protocol. That's where the model gets those few examples right before it needs to perform the new task. But the key Seal difference is how it adapts. Instead of relying on preset rules or human-tuned settings for, say, data augmentation or optimization parameters, Seal autonomously configures its own adaptation pipeline. It generates a self-edit that specifies exactly what to do. Like, okay, for this task, apply these specific image rotations and flips, or use this particular learning rate, train for these many epochs, calculate the loss this specific way.
Wow. So it's literally deciding the best way to train itself for that specific new task on the fly. It's choosing the learning strategy, not just absorbing the data. How did that work out? What were the results for this kind of self-configured few-shot learning?
They use Llama 3.21b instruct on a specific subset of ARC tasks designed for this kind of evaluation. Seal achieved a 72.5% adaptation success rate, which is pretty significant. Compare that to standard in-context learning with the same examples that got 0% success on these particular tasks. And TTT, without Seal's RL optimization beforehand, only got 20%. Now, it's not perfect. An Oracle TTT, meaning a human expert carefully selecting the absolute best settings, gets 100%. But going from 0% or 20% up to over 70% autonomously, that's a really big leap. Shows its versatility.
Yeah, it definitely sounds powerful. Almost like these models are getting, well, agency in their own learning. But, nothing's perfect. Every new approach has its challenges, its downsides. What are the main limitations or hurdles for Seal right now?
Yeah, absolutely. There are a few important ones to keep in mind, and they're pretty common themes in advanced AI. First up is catastrophic forgetting. This is a classic problem. As the model keeps learning new things sequentially using these self-edits, it can start to perform worse on stuff it learned earlier. The current Seal setup doesn't have an explicit mechanism to optimize for retaining old knowledge while learning new things. It's focused on adapting to the new input.
Right, the age-old problem. Learn something new, forget something old. Is that just baked into the process, or are there ways around it, and what else?
Well, it's a major research area, finding ways around it. It's not necessarily a fundamental limit, but it's hard. The second big hurdle is computational overhead. That inner loop where it has to fine-tune and then evaluate the model for every single potential self-edit to get the reward signal. That's computationally pretty heavy. They mentioned each evaluation takes something like 30 to 45 seconds. Doesn't sound like much, but during RL training, you do that thousands of times. It adds up to a lot of compute time and cost.
Okay, expensive. And the third limitation?
The third is what they call context-dependent evaluation. Right now, Seal kind of assumes that every time it gets new information, it also gets a specific task to evaluate its performance on. Like for knowledge, it gets question-answer pairs. For few shot, it gets test examples. This makes calculating the reward easy because you have a clear target. But it limits how easily you could apply Seal to just, say, a massive dump of unlabeled text from the internet where you don't have those pre-made evaluation tasks ready to go.
Gotcha. So forgetting cost and needing specific evaluation tasks, what's the path forward? Do the paper suggest ways to tackle these?
Oh, yeah, definitely. And the ideas are pretty exciting. For catastrophic forgetting, they suggest things like shaping the reward signal, maybe penalizing the model if its performance drops on older tasks, or integrating more advanced continual learning techniques, maybe things like trying to make edits in ways that don't interfere with existing knowledge, like null space projections or superposition ideas. And for the evaluation problem, this is really cool. They suggest enabling the model to generate its own evaluation questions right alongside its self-edits. If the model can create its own relevant questions about the new information it's processing, it can essentially create its own supervision signal for the RL loop that can make it much more scalable to general unlabeled data.
Generating its own tests. That's quite something.
Yeah. And if we zoom out a bit, think about the bigger picture. The authors point out this projection that, we might run out of high-quality human-generated text data for training these massive models maybe as soon as 2028. This data wall means we absolutely need new ways to keep improving LLMs. We can't just keep feeding them more internet text forever.
That's a really critical point. If human data runs dry or becomes less effective, where does that next level of capability come from? Do models just hit a ceiling?
Oh, this is exactly where frameworks like Seal could become not just interesting, but potentially essential. You can imagine a future where an LLM reads, say, a new scientific paper, or maybe gets data from interacting with the real world, and then it doesn't just store it. It actively generates maybe thousands of implications, explanations, test questions, and structured training examples for itself. This loop's self-expression, self-evaluation, self-refinement could let models continuously improve, maybe specialize in complex areas, without needing constant human-curated data pipelines.
That really does feel like a paradigm shift. Models aren't just intelligent tools anymore, they're becoming autonomous managers of their own learning process, almost designing their own curriculum. It points towards systems that can learn incrementally from experience, modifying themselves to get better aligned with the world they interact with. The whole idea of an LLM as its own teacher, constantly refining its internal knowledge. It really changes how you think about their potential. It really makes you wonder, doesn't it? What happens when the student becomes the master of its own education? Well, that's certainly a lot to think about. Thank you for joining us on this deep dive into self-adapting LLMs. We hope it's given you some valuable insights.